For that, let's now look at the actions. We can find in here what the equation for the derivative of the argument of pericenter is going to be. That would be the derivative of the Hamiltonian with respect to the action J2, the angular momentum. Now, to take this derivative, we need to write then the Hamiltonian in terms of the actions. Well, that is relatively simple. We just needed to convert the orbital elements to actions. We know that J1 is equal to the square root of mu times A, so we can rewrite A as J1 squared over mu. And because J2 is J1 times the square root of 1 minus Z squared, then you can write the eccentricity as 1 minus J2 over J1 squared. And because J3 is J2 times cosine of the inclination, that's simple enough. So the cosine of the inclination is J3 over J2. Therefore, the sine of the inclination squared is 1 minus J3 squared over J2 squared. If you do these substitutions, we can rewrite the Hamiltonian in terms of the actions. Now, if you do these substitutions between the orbital elements and the actions, you can rewrite the Hamiltonian in terms of the actions. And now we can take the derivative of this in terms of J2 to find the variation of the argument of pericenter. That leads to, now let's flip a page. Now the system has a root. You can set this equal to 0 and find when this term is going to be equal to 0. So to find this root, we set first sine square of omega to be 1. So that means omega is at plus or minus 90. And then the root is going to be found of the solution of this equation for the actions. Now let's solve this then for the actions. J2 over J1 is the same here. So this is then, you can solve this for J2. Now let's convert back to orbital elements. Substitute the J2 here. Substitute first the J3 by its expression depending on J2. Extract J2. I'll cut and we have then a square root on the other side. Now square this. And substitute the J2 as its dependence on J1. So this is then the square root of 5/3 J1 times cosine of I. Substitute now J2 as is dependence on J1. You get rid of the J1 on both sides. So if you start from an orbit of 0 eccentricity, this defines you a critical inclination. Set the eccentricity to 0, and then you have a critical cosine, which is the square root of 3/5. That gives you roughly 40 degrees. This gives the critical angle to excite Kozai-Lidov oscillations. And indeed, this signature of 40 degrees of critical inclination is exactly what is seen in the irregular satellites of the giant planets. Beyond that, you start to not have stable satellites, either on the prograde or on the retrograde 40 degrees away. So you see here in this phase diagram, on the y-axis, you have 1 minus eccentricity squared. So circular orbits are at 1. And more eccentric orbits as you go lower in this number. And then on the x-axis is the argument of pericenter. We found the roots by setting first the sine squared of the argument of the pericenter to be equal to 1. That corresponds to this line here of 90 degrees. You don't need to set that equal to 1. You can solve the equation for any argument of pericenter, which is what is done here. And you find that beyond the separatrix, you have circulating orbits, orbits that go for all arguments of pericenter. But inside the separatrix, you have closed loops. These orbits, they can only have a finite range, a closed loop of argument of pericenters. These are the Kozai-Lidov oscillations. You see that the eccentricity is varying, is also doing oscillations here within this range. And this separatrix is the critical inclination of 40 degrees. Now we're using the example of planets, but Kozai-Lidov oscillations are, as an effect of dynamics, they are pretty common in other systems too. One example would be binary black holes orbiting in an AGN disk, where you have the distant perturber being the central supermassive black hole in the center of the AGN. If you have a binary black hole and they are in an inclined orbit, they are going to also execute this Kozai-Lidov oscillations. And one of the interesting things that is happening here is that can facilitate the collision between them, because when the eccentricity gets excited to very high values, close to 1, these two black holes get very close to each other. They emit gravitational radiation very intensely when they're close, and that makes the orbit decay. The classic Kozai-Lidov oscillations have constant energy, but if you have a mechanism to dissipate energy, you can make the bodies collide. In this case, that's the emission of gravitational radiation. Other example would be mergers of neutron stars. The same thing can be happening. If you have very wide orbits, you can wait for several Hubble times for the orbits to decay just due to gravitational radiation. But if you have a third body, if you have a triple, the inner binary can execute Kozai-Lidov oscillations, get to high eccentricities that get them to closest separation. And even if they don't collide immediately, they can get close enough so that at the pericenter, the emission of gravitational waves is very intense, and they start to get closer and closer. Kozai-Lidov oscillations with dissipation of energy is one of the prime channels for contact. In fact, I wrote an argument last year arguing that a channel for Arrokoth to have come into contact is for Kozai-Lidov oscillations. The system might have started as a wide binary with a high inclination, and through Kozai-Lidov oscillations, that the eccentricity was pumped. And in this case, the dissipation came from the aerodynamical drag in the solar nebula. There are other cases also of contact binaries. This is the comet that was visited by the Rosetta spacecraft. As you see, this is a contact planetesimal, again, two bodies that got into contact. In this case, the mechanism might have been Kozai, or it might have been simple, other types of three-body interactions, but it's possible that it was also due to Kozai. Now, Kozai has been heavily studied in exoplanets because there are several systems where you have a distant companion. For example, this system here has a distant star and two giant planets. It's conceivable that this distant binary is forcing the system into Kozai-Lidov oscillations. And indeed, many hot Jupiters are seen to have inclined orbits with respect to the equator of the star. The situation for that to occur is you can have a distant body, and that distant body is forcing the inner planet into Kozai-Lidov oscillations.